This is Math 152. We're looking at 2.5, part 1. And we're going to talk about density functions. So, first off, just imagine that you had some just rod. And I'm going to line it up along an x-axis. So, like, there's my x-axis. Let's have it run from 7 to 10. And we want to know its mass. And so, one thing that could happen is everything is just like all the materials distributed equally through here. So we could say that this has a density of, let's say, just 5 pounds per unit. So every unit is 5 pounds. So if that was the case, if that density was evenly distributed, it's really easy to figure out the mass of this. Every 1 unit is 5 pounds. So this is 10 to 7. So 10 minus 7, right? That's how many units times 5, and that would be 15 pounds. So pretty straightforward. But what if this density is not constant? Like, what if it's distributed in a way, and we could write, say, an equation for it? That's what we're going to get at. So whatever that density function is, we're just going to write it like that. That is going to be our density. So let's say, for example, that the density function for this is 1/3 x squared. So in other words, the further we get from 0, the denser this thing gets for some reason. So at 10, kind of the instantaneous density is 1/3 times 10 squared. So notice that it is not evenly distributed. So this idea of like 10 minus 7 times whatever, well, the x value is changing. So what would we multiply it by? So hopefully you're thinking, hey, we're in a calculus class, so we have a good idea what we could do with this. So let's keep those same parameters there, and let's just think about just some little slice out of here. Right? We could have this slice, and really we're talking about a rod, like there's some width here. We're treating it like it's a one-dimensional shape, right? It's just like a little piece of a line. So we have this, and we have that little distance. We'll call it, that's the change in x. That's how it is. And notice, like at some x point, I'll call that x sub I, we have that change in x. And that change in x is, it goes from one x to another, right? It goes from like x sub I to a little more than x sub I. You might say x sub I minus 1 or something like that. And since we're calculus, think about, we're going to let this get really small, so we can just say we're at that spot. So a good estimate for the mass just of that little piece would be the density function at that point times that change in x. Now it would be a little off, right? Because the density is changing from here to here, but if this is sufficiently small, it's going to be more and more accurate. And then what we would do is we'd say we're going to cut this up into a bunch of pieces. So we have a bunch of these different I values. There's that mass, and we're going to add them all up for a bunch of n's, right? Like if n was 15, we'd be cutting it into 15 different pieces. And again, calculus, let's let that limit go to infinity. And this becomes a to b. In this case, it's going to be 7 to 10 of our density function times our change in x. Yeah, so in general, if that's our density function, our mass is the integral across whatever our range is of the function times that change in x, right? Because the function tells us how dense it is there. Change in x gives us a little bit of a width, but we're going to let that change of x get infinitely small, so it becomes dx. So in this case now, if that thing was changing, right, that density is changing as x is increasing, we now can figure out what this would be. Whoops, I'm going to do the integral. I'm going to get this. So this would be that, which would be 73. And I didn't define units, you know, it might be pounds or ounces, some measure of mass, but we'll say units. Yeah, so here's another example. We have some, we'll call it a rod, and its density. We want to know its mass. Right, so we have this. So we have this little linear thing right here. It's running from 1 to 3. We know that this formula right here. Actually, let's do that. This formula right here describes the density at a given x value, right? So at 2, the density of this is 2 times 2 squared plus 3. This is, like the last one, getting more dense as we go this direction for whatever reason. And we want to know the mass of this thing. So let's set it up. We're running from 1 to 3. We're going to let this change, and we know how to deal with that. And if we shove that into a calculator or whatever we're going to do, we'll get 70 thirds. That's like 23 and a third units. It's interesting, this density function, again, what it's saying is this thing gets more dense, right, as this increases. We could have had a different density function. We could have had something like that, say, which is kind of interesting because at 2, this says the density is 0. And so from here, it would kind of decrease and then increase back up, going back towards 3. So, you know, it doesn't have to be constantly increasing or decreasing, but we do have to have some predictability to it, of course, to run it into our integral. So that's this idea of this linear density. And now what I want to do, take this idea, this is one-dimensional, and let's go two-dimensional with it. And now we're going to set up our x-axis again, but we're going to nestle our rod against 0, and it's going to come out here and have a certain radius r. So we've got that. And let's add a dimension. So now we've got our y-axis as well. And we're just going to rotate it. That's a radius. So we are going to rotate it around. And as it sweeps out, it just leaves area in here. So notice now we have a disc or a plate, basically. And this rod here, what this gives us is the radial, like radius density. And as it comes around, now we have an area of this whole plate, of this whole shape. And so now we're finding the area mass off of this density. Notice, like, if this is super dense here, as it rotates around, that density happens too, right? And if it's less dense here, that happens here. So the density kind of happens in these rings. So what I want to be able to do is find the mass of this disk, or a plate, however you want to think about it. So in other words, if I just take a little cut in here, got this little change in x, think about it, and I just take that around, it gives me this strip. So like we've done before, if I pull that strip out of there, notice that, like, I have this x value, which is the radius out to it, that distance right there. And then I have this strip, which is my change in x. And that width is going to give me the density, right along there. And again, whatever the density is, plug x into that and multiply it by that change in x. That gives me a good estimate for it, this area. And then I want the area of the whole thing. So think about cutting it. Cut it here, stretch it out, just so you can see where this formula comes from. Cut this and unwind it. This right here is the density at that spot times that width. And then this right here is basically the circumference of that circle, which is 2 pi r, where the radius is x. So 2 pi times x. So the area of this rectangle is length times width. So what I can say then for my formula for the mass of the disk, I'm going to run x from 0 to r, right? I've centered it at 0, 0. And then I'm going to take the area of this shape, so 2 pi times x times the density function times the change in x. And this becomes dx because basically we let that get infinitely small. So there's that piece. So just like the only difference, notice, is what we're doing mass just of the radius is just that, right? It's just the density function times the change in x. But then now, since we're doing it for a circle, it's that times this distance around the outside, this circumference. So just to do an example, so we can use that relationship. So we have this density, this radial density function of a disk. So again, that function tells us how dense this is, depending on the x value. Let me slap an xy on. We know that the radius is 4, so this is getting out here to 4. And it's a disk, so that radius spun all around, and we're trying to find the area of this thing. So we're taking this cut, taking that little shape right there, and we know that this is the density function times the change in x, and this is the circumference at that x value, so 2 pi times x. So we are running from 0 to 4, and it's the area of all these strips added up together. So area is going to be pi times x. Oh, we know what that is. That is square root of x. And now we can deal with this integral. I'm going to take that 2 pi out of there. I'm going to think of this x. This is x to the 1/2. This is x to the 2/2. So x to the 3/2. You can do the rest of this one. Get on out, just so you know, I get 128 pi over 5. Don't forget about that 2 pi. All right, give those a try. Send me questions, message me, or post them in the forum.